Okay, so now we have least square approximation that help us to find coefficients for a given number of for a given set of independent variables. And once we have a formula, we have some ways to validate that formula, right? So we're pretty good. Now we're going to introduce you one more thing. It's about variable transformation, which allows you to consider a lot of different kinds of relationships between independent and dependent variables. And given that there are so many possibilities, we need to consider variable selection so that we can decide how to form our regression model. Okay, so let's start. Recall that we are talking about house prices. House prices. We have one column, house size, the other column for house bedrooms. We probably also include the house ages, which is measured in years, as another column or another independent variables. Because indeed, the age of a house may also affect its price. Okay? So when you consider that, when you think one variable may affect the other, drawing a scatter plot is typically a good idea. According to this sample data set, we think that, when the age when age increase, price decreases, right? Price decreases when we have a larger age. So it seems to us that indeed age has an impact on price and it's a negative impact. So anyway, I want to see how this happens. So let's add age as an independent variable in explaining house prices. Okay, and in the following try and errors, in the following trials, because the number of bedrooms seems to be unhelpful, now let's ignore it. Let's ignore it in this video. So now, for house I, yi is the price, x1i is the size, and x3i is the age. Then we consider the following relationship. Here we still assume that it's a linear relationship. That means we think x3i has a linear impact on yi in this linear format, in this linear equation. We want to estimate beta 0, beta 1, and beta 2. Beta 2. Okay, so a typical regression work. Software would give us the following table. Blah, 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 blah. So what does that mean? So every time when we look at a table like this, we first check stars. When we see stars here, we're happy because that means both variables have an impact on the final price. We see that this p-value is quite small. For age, the p-value is not very small, but at least is smaller than 10%. So it's believed to be useful. We also have their coefficients. When the house becomes larger, the price goes up. When the age becomes larger, the price goes down, which also makes sense, right? So everything seems to be fine. And even better is that R squared goes up from less than 50% to above 60%. Also, you may verify that the adjusted R squared also becomes larger. So that means we add one meaningful variable into our model, and that variable allows us to significantly improve the power of explanation of our regression model. Okay, everything looks fine, and indeed that's good. Indeed that's good. So, what's next? The next thing is to ask whether we may do better. Okay, many people would look at this scatter plot and think about their intuition and then make one conjecture. That conjecture is that maybe the impact of age on price is nonlinear. Why is that? We probably guess that when a house is new, the value would depreciate a lot when the house is new. But when the house is old enough, then being one additional year old probably has no impact, or the impact is very small. Or at least we know this is true for used cars. When a car is old, then getting even older has no impact. But when a car is new, when it gets 1 year older, the value would depreciate a lot. Or if we look at the graph, well, it seems to us that the relationship is something like this, right? Seems to be nonlinear. So that means it's worthwhile to try to model this nonlinear relationship. So one possible way to do that is to replace house age by its reciprocal. Okay? Previously, here we put x3i. Now let's replace it by its reciprocal. Then that means we are trying to capture the fact that when x3 goes up, yi goes down in a nonlinear way. And once we do that, we now again can try to estimate beta 0, beta 1, and the beta 2, and then try to compare whether this is a better alternative. Okay? But the key is that we may add a variable, or we can create a new variable from existing variables, and then measure whether there is a relationship between the dependent variable and our new variable. Okay, so that's something we can do. To do that, now we need a few steps. So first, we need to prepare a new column. We need to do it by ourselves. Otherwise, we don't have that set of data. So we need to create one more column. Let's call it 1 over age. And then we can just calculate that from our age column. So we get all these numbers. And then we input the 3 columns here into a software to get the report. So basically, we still use software to do the calculation, but you need to prepare this column by yourself. Once we do that, then we get the report, and then we can see whether this is good or not. In general, we may consider any kind of nonlinear relationship. Does not need to be this one. For example, you may even want to try, okay, then if we can try x3i over 1, how about x3 square over 1 over x3 square? Okay, and there are all kinds of things that you may try if you have a reason. But that means you can try any kind of nonlinear relationship. This technique is called variable transformation. You have some existing variables, you transform them to new variables, and use new variables as predictors. Well, let's see how good the new model is. We get a different report. Still, they are significant. We have p-values. One is less than 5%, the other one is less than 10%. Good. We have their coefficients. Now the coefficient here cannot be interpreted in the easy way when we have that linear relationship, because now this number is hard to interpret, but still at least we see it's positive. So what does that mean? When age goes up, 1 over age goes down, right? And the coefficient is positive, so that means the price would go down. So we see that age has a negative impact on price, which is reasonable. Okay, still we can use this coefficient to form a formula so that in the future when we have a new house, we can use this formula to do a prediction. So that can still be done. Now let's talk about the overall quality. We already know that variables are both significant. If we use size and 1 over age, R squared and R adjusted square is here, okay, around 68% and 62%. That's good, but actually when we were using size and age directly, R squared and the adjusted R squared are actually higher. So at least for the given set of data, using size and age instead of using size and 1 over age is better. So this somehow violates the previous intuition, right? But of course, that's possible because no one says intuition must be right. So that means the intuition that house value depreciates at different speeds is not supported by the data we collect. Of course, it may be true, somewhere, somehow. It may be true, but at least our data do not support that intuition. Either we conclude that, well, the intuition is wrong, or we conclude that we need to collect more data. So it depends. But anyway, what we can say at this moment is that our data do not support that intuition. If we need to choose a model to do prediction, we should choose size and age directly and believe that age has a linear impact on price. Okay, so that's the idea. You may try a transformation, but you still need to compare whether that transformation is better or worse.